Welcome to my shop. Today we're going to discuss Lenz's law as well as some aspects of inductors and how inductors react in an AC circuit. Now, Heinrich Lenz was an early pioneer in the study of electricity, and he developed a law that simply states an induced voltage or current will oppose the motion that created it. Now that seemed kind of like an oxymoron, but I am going to demonstrate that. Now in my demonstration, I'm going to be using this length of copper pipe that also features a channel that has been slotted so that my viewers can actually see what is happening during my demonstration. In the demonstration, I will be using a glass marble as well as a spherical magnet. Now, the marble and the magnet are not identical in size, but for the purposes of this demonstration, it will suffice. Now, what we're going to do in this demonstration is alternately, I'm going to be dropping the glass marble through the pipe, and what we're going to do is observe how fast the marble falls through the pipe. I'm then going to follow that up with dropping the spherical magnet through the same pipe, and we're going to observe how long it takes for the magnet to come through the pipe. And we're going to do a comparison. Here, we're going to drop the marble through the pipe. Now, as people may expect, gravity is going to work in our favor here. And as I drop it, I'm going to try and catch it. And we can see that in less than a fraction of a second, the marble falls through the pipe with gravity aiding it. But now, when I drop my spherical magnet through the same conduit or channel, what I predict is going to happen is that the magnetic flux emanating from this marble is going to start to induce a voltage and current into the walls of the pipe all the way through. And according to Lenz's law, if there's an induced voltage, it's going to oppose the motion that creates it, and it's going to slow the marble down. So let's see. Here it goes. And what we should be able to observe is that the marble is falling, but at a slower rate than the glass marble I used previously. So let's do that again. While I didn't time it, I can tell you that it probably took in excess of 3 seconds as opposed to the fraction of a second it took for the glass marble. Besides being a parlor trick, there's a little bit more to it than that. From this, in the study of electricity, they went on to develop or take this concept a little bit further. And so when we start studying inductors, meaning coils of wire, there's also an inherent characteristic is that inductors will always oppose a change of current. Now I've got a demonstration set up on my bench over here, and so I'm going to move over to the bench and we'll talk about this a little bit further. Here at the bench, what I've done is I've got a variac which allows me to adjust the input voltage for this coil that we have here. I've got 2 multimeters. One is going to be set up to record the current that the coil is going to be drawing from the circuit, and this one will be recording the voltage. And what we're going to do is we're going to kind of go through the math of what happens with an inductor, as well as some of the characteristics. Now, first things first, I'm going to do is take a resistance reading of this coil prior to doing anything, because we're going to need that piece of information in some of our future calculations. So I will turn the meter on, and let's see here. I'm getting 0.7 of an ohm. I've currently set up this first multimeter to read current, as we can see by the connections, and I've labeled it. I've also set up the second multimeter to read the voltage coming from the variac. And here we have the coil. Now, the coil was measured at 0.7 ohms, and you'll notice that it also has this ferromagnetic core. We're going to put the core inside of the coil, and you can see it slides in there nice and freely. Now, I'm going to turn on the power supply. Now, the power supply is fused at 10 amps. The same thing with my multimeter here. It has a 10 amp fuse. So this is what's going to govern how much voltage I'm going to put into the circuit so as to not blow the fuses in both of my pieces of equipment. So here goes. Let's turn this on. And we can see that we're starting out with 6.3 volts, and this coil is already drawing 2 amps. I need to bring the voltage up, and I'm going to do it slowly. And my goal is to bring the voltage up to about 22 volts. I'm not sure if the camera can pick this up, but the coil is starting to hum. And I'm getting closer to my target of, I have to be there we are, 22.1 volts. Now I'm going to record that information as well as the current, which is 8.13 amperes. I have to work quickly because of the fact that this coil is starting to get hot and I don't want to melt the plastic body. One curious thing is watch as I try and withdraw the coil and how it affects the current. You can actually hear how the coil is starting to hum much stronger, and that my current is steadily climbing the further I try and withdraw it from the coil. But if I let go, I should get my finger out of the way, but as I withdraw it, it goes and it snaps right back in. Now there's no spring inside of here. What's happening is Lenz's law, that phenomenon that says that inductors will naturally oppose a change of current. And this is what's happening. As I try and withdraw it, I'm affecting the impedance. And the inductor is naturally trying to oppose it, and it wants to maintain its natural state. Let's turn this off before I melt everything. And let's start looking at the math and the theory behind this. Okay, now that we've turned off the power supply and we have all that equipment put away, let's get down to the math. In front of us, we can see the Ohm's law triangle, as well as all of the values that we've measured. The resistance of the coil that we measured prior to starting, so this was taken before there was power in the circuit. We measured the current at 8.13 amperes, and the voltage was measured at 22.16 volts. Now, there's a couple things I would like to do. The first thing is I'd like to confirm the amount of current we should have read using the Ohm's law formula. Simply said, if I put my finger and I cover up the I, which represents current, you'll see that I will take the applied voltage and I'm going to divide it by the value of resistance. So let's do that. So the formula is going to be I is equal to E divided by R. We're going to plug in our values, 22.16 volts of AC. We're going to divide that by 0.7 ohms. Punching these values into my calculator, I'm going to get, as a result, 31.66 amperes. But at first glance, there seems to be a problem here. This is almost 32 amps. Now I know for a fact that the power supply had a fuse at 10 amps. and so did the multimeter. And during the whole demonstration, I never lost power. I never damaged any of the fuses. So is this a mistake, or is there more to this than meets the eye? Let's try calculating the value of resistance, the overall resistance for the circuit. Now, simply put, if I go back to this, if I cover up the R, we're going to take the applied voltage and we're going to divide it by the current. So the formula is going to look like this. R is equal to E divided by I. Again, 22.16 volts AC. This time, we're going to divide it by the 8.13 amps, which we measured. And I know that that's correct because of the fact we never blew any of the fuses in the multimeter or the internal fuse of the variac. Putting these values into my calculator, 22.16 divided by 8.13, I get 2.725. Now, I'm going to round to 2 decimal places, so I'm going to end up with 2.73 ohms. Now, is this a value of resistance, or is this something more? It is something more. What people fail to realize is that, yes, we measured 0.7 ohms of resistance in the coil, but when we started running power through it, meaning voltage and current, a phenomenon occurred is that this coil, which is an inductor, was actually inducing a voltage into itself. Inductors are actually devices, and here's another coil, that are a reservoir for magnetic energy that is constantly in a state of change or flux. And because of the frequency of the applied voltage, which was AC, it was inducing a voltage into itself, and that voltage was creating a counter voltage that acts an awful lot like resistance, but we call it inductive reactance. And inductive reactance and resistance combine to form a new value, and that is represented by the letter Z, and we call that impedance. Now, impedance is not calculated based on Ohm's law so much as impedance is derived from the following formula. Z is equal to R squared plus X sub L squared and the square root. Now, R represents resistance, X sub L represents a value of inductive reactance. This phenomenon where the coil is inducing a voltage into itself, and that needs to be accounted for in these calculations. Now, we're going to have to modify this formula in order to calculate the value of inductive reactance. We do have a value of impedance right here, 2.73 ohms, and I do have another value of the 0.7 ohms of resistance. It's just a matter of rearranging this formula to calculate the value of inductive reactance. And so that formula is going to look an awful lot like this. X sub L is equal to Z squared minus the value of R squared and square root. So now we're just going to put in the values we've calculated. 2.73 ohms squared, subtract 0.7 ohms, which we've measured, and I'll just get a ruler here, and we can't forget to do the square root of that. Plugging these values into a calculator, for the people that are following along with me, 2.73 squared, subtract 0.7 ohms squared equals, and then I will square root that answer for a total of 2.64 ohms. At first glance, what it should show is that the value of resistance is somewhat small in comparison to the value of inductive reactance. So the inductive reactance has a major role to play in controlling the amount of current flow in the circuit. It's really important that tradespeople or anyone working in the electrical trade, working with electricity on a daily basis, has a sound knowledge of what happens when we're working with inductors, such as this coil that we use in our experiment. We saw that when we tried to withdraw the ferromagnetic core from the coil, we observed that there was a spike in the current. Why was there a spike in the current? Because of the fact we're playing with the impedance of the device. This was an iron core inductor, and the magnetic flux density was significantly higher. When I started to withdraw the ferromagnetic core, it was going from an iron core to an air core, and the magnetic flux of an air core inductor is a lot weaker, and as such, the coil was not inducing as much inductive reactance as efficiently as it was when it had the iron core. As a result, the inductive reactance went down, meaning by extension the impedance went down. And we know by studying Ohm's law that current and impedance are inversely proportional to one another. If my impedance goes down, that means by extension my current that the device is going to absorb is going to go up. And that's what we saw in this example. It is of concern and noteworthy that people have to understand that impedance, inductive reactance, resistance, voltage, and current are all interrelated to one another. We can't affect one without seeing a ripple effect in something else. And it is our responsibility as electrical workers to have a real sound understanding of what that means. I hope as a viewer you found today's topic interesting and helpful in your understanding in the field of electricity, especially how inductors will act in a circuit. Until next time, please stay safe.